Okay, so handing over to our host with the most, very briefly, Professor Emma Sokol, who's going to be guiding you through our talks for this morning. And she has done tremendous work putting together the program and liaising with Institute of Physics. So over to Emma.
Thanks, Paul. And I'd just like to reiterate the thanks to Joe for making this available to us, because we couldn't have done it otherwise. But right now, it's my great pleasure to introduce our first speaker, who's George King, who's Professor Emeritus from the University of Manchester. He's working on his third book, but the topic of the second one is the physics of energy sources, and he's going to talk to us about solar energy and a bright future. So thanks very much, George.
Thank you, Emma. Good morning, everybody. It's a great pleasure to be here and a great honor as well. I've been to UCD many times, and it seems that the sun is always shining in UCD. And as the sun passes over the equator for the autumn equinox, then sure enough, today is a lovely autumn day as well. And of course, the sun is our main source of energy. And today I'd like to talk about solar energy, which has a bright future. And the message is that the solar power reaching the surface of Earth, 10 to the 17 watts. And that's an awful lot of electric light bulbs. It's the amount of energy, or the amount of solar energy received in 1 hour is as much energy as the whole of civilization uses in 1 year. And then it's our job as scientists, physicists, to collect this energy as efficiently as possible. And when we talk about energy, maybe, or it's useful for me at least, to think about light bulbs. Well, 100-watt light bulbs you don't see so much anymore, or 1 kilowatt fires and how long they would be provided by energy. So I might talk in terms of 100-watt light bulbs and 1 kilowatt fire heaters. So the outline of my talk, I'd like to talk about the physics of the origin of solar energy at the center of the sun, and how that comes to us then as sunlight from the black body radiator that is the sun. Its journey to Earth, and mostly its journey through the atmosphere, and what the atmosphere does as it comes through the atmosphere, and also as it goes out of the atmosphere, escapes from the Earth also. And then I'd like to talk about how we might harness solar energy. And in particular, I'll talk about solar heat collectors, which we literally heat a plate and collect the energy that way, which is transported by a series of pipes in the plate. And that provides us with heat. Heat, water, temperature, maybe 70 or 80 degrees. And we can compare that with a solar cell, photovoltaic cells. And I suppose the major difference is, with the solar cell, what we obtain is electricity. And I'd also like to say something about energy storage. Because, of course, the sun doesn't shine all the time, and windmills don't turn all the time, and how we might store energy on an industrial scale. Solar energy, one of its advantages is that it's a renewable energy source. And this simple cartoon just illustrates that point. That if we have an oil well or even a mine of uranium, then they have a finite lifetime. But solar energy is a continuing flow of energy that provides us energy for us. The sun will shine for 10 billion years, and we're about 5 billion years into that space. So fortunately, we've got 5 billion years left of renewable solar energy. And solar energy, solar radiation, is the result of nuclear fusion in the core of the sun. So let me say a few words about that. Our friend Einstein is perhaps the most famous equation in physics, energy equals mc squared. And the reaction which is happening in the center of the sun, there are 4 protons, 4 hydrogen nuclei, combine together to produce an ion of helium. The temperature is so high that all the matter is in the form of ions, and in fact it's gaseous hydrogen and helium. So if we work out the masses of the 4 protons, the mass of the helium, then what we find is that we get 27 million electron volts of energy for each helium that's produced. So when we burn coal, the sort of energies we're dealing with are energies of electron volts, perhaps a few electron volts. When we talk about nuclear reactions, we're talking about millions of electron volts. So a factor of 10 to the 6th higher. So whenever we compare the energy we can get from conventional sources like coal or oil with nuclear sources, then it's that power of 10 to the 6th which keeps cropping up. So a kilogram of hydrogen, for example, would power your electric fire for 20,000 years. A kilogram of wood would probably keep the equivalent to keeping the fire going for maybe 5 hours. And that occurs in the sun at a temperature of 10 to the 7 degrees. And that in a nutshell is the problem with nuclear, or the development of nuclear fusion. When I was a student, a bit more than 30 years ago, then I went to a lecture on nuclear fusion, and the speaker said, nuclear fusion, 30 years hence. So last year I went to a lecture on nuclear fusion, and the speaker said, 30 years hence. So it's always 30 years ahead on the horizon. Anyway, in the center of the sun, we have this high temperature, 10 to the 7 degrees. And in the reaction, we are producing very energetic photons. We're producing X-rays. And those X-rays, those photons, high-energy photons, diffuse from the center of the sun to the surface via a process, via a random walk. So, if I take n steps, then I take nl distance. In the random walk, what we do is we take a step, we flip a coin, and if it's heads, we go in one direction. If it's right, we go in the other direction. It's the drunken sailor problem, also worked out by Einstein. So instead of going n steps, the distance we go is root n times the step length. So the d is the distance traveled, L is the step length, which we can approximate about 1 millimeter in this process of the photons coming from the center of the sun. So the number of steps is this expression here. Each step takes the step length divided by the velocity of light. And if you put the numbers in, we get the total time it takes. And what you find is that those photons which are produced at the center of the sun take maybe 50,000 years to get to the surface of the sun. And in each of those collisions, they are losing energy, they're scattering off electrons. So the X-rays at the center of the sun become visible photons when we reach the outer photosphere of the sun. Fortunately, those X-rays are shielded from us here on Earth. But 50,000 years. The neutrinos that are also produced might take 1 or 2 seconds to leave the sun. Photons take a lot longer. Now, it's often said that at the end of the 19th century, physics had done all it had to do, and all that was left were the decimal points. But that's not actually true, because there's a lot of unhappiness and uncertainty in physics, because classical physics wasn't explaining for example, the specific heat of a gas, and something had to change, the birth of quantum mechanics. The people who were involved, or some of the people involved, I put here, Wien, Boltzmann, who was so dismayed by the arguments and the reaction against him that eventually poor Boltzmann actually committed suicide in 1906. Max Planck, of course, one of the pioneers of quantum physics. And there's Pink Floyd in 1973, showing the spectrum, the solar spectrum. Okay, so Wien, his displacement law. So it sounds like a very mundane experiment. You have a furnace with a hole in it, you heat the furnace up, and the radiation comes out, and you measure the spectrum of light which comes out. It sounds like a very mundane experiment, but in fact, of course, it changed the face of physics. Because what happened was that classical physics couldn't explain the shape of this spectrum. And it was Planck who had to quantize the energy of the particles in the furnace. And then, of course, Einstein went one step further and quantized the energy of the radiation field, the birth of the photon. So Wien had this simple expression here, that the peak in the wavelength, the peak wavelength in the spectrum was related to the temperature of the source. So now, if we look at the solar radiation, if we look at the solar spectrum, straight away we can deduce the temperature of the sun. Stefan and Boltzmann, they had their law where the power was proportional to T to the fourth. So if we know the temperature, we know the size of the sun, then we can work out how much energy the sun is emanating. And it's something like, on this sun's surface, 6 kilowatts per centimeter squared, and that total power. And of course, it was Planck who first described the shape of this curve, first of all empirically, but then theoretically when he input the quantization of the energy. Okay, so this is a simple model of the sun and the Earth. It's a first year problem we give to our students. And in this model, we try to work out what's the equilibrium temperature of the Earth. And the idea is that we know Stefan's law, we know the temperatures, we know how much energy is emanating from the sun. That's going to fill a sphere, and that sphere is the distance between the sun and the Earth, which is quite topical at the moment because, of course, Captain Cook on the ship Endeavour went to Tahiti to get a good measure of that Earth to sun distance exactly 250 years ago. So this is the idea. The Earth absorbs the energy, and at equilibrium, the Earth has to radiate that amount of energy. Now, in fact, the Earth absorbs about 70% of the energy it receives from the sun. So now we can just use this factor of 0.7, and we can use Stefan's law, the dimensions of the involved, the distance of the sun, the size of the Earth. So there's our sphere at the sun-Earth distance. That's the amount of area that is intercepted on the sphere. That's our disk, if you like, of the Earth. And that must be the amount of power that's radiated. So if you work out what that is, what we obtain is an average temperature of the Earth of a chilly minus 17 degrees. So thankfully, the greenhouse effect, global warming, the right amount, actually increases that to something like plus 14 degrees. And what we've got there, of course, is that the atmosphere is acting like a blanket. And this slide here shows the spectrum of the solar spectrum, back to Pink Floyd there. And the temperature of the Earth is 300 degrees, absolute. So a black body at 300 degrees emits radiation in the infrared. So all of us here are emitting radiation in the infrared. And the idea is that, well, the atmosphere, as the astronomers will know better than me, has certain windows in it to let the radiation through. And of course, that's where traditional astronomy lies, in the visible, in the radio frequency range. So this is the light coming from the sun. And this is the radiation that the Earth is emitting. And this is the order of a few tens of microns. And the idea is that the atmosphere is transparent to visible radiation. Most 50% of the Earth's energy is coming into the visible. But the molecules, when the Earth emits the radiation, they've got various molecular vibrational motions. And each one of those vibrational motions can absorb energy in the infrared. So when that radiation comes back from the Earth, then that radiation is absorbed by these molecules, which then can send energy back to the Earth. And if the Earth is receiving more energy, then of course its temperature must increase to maintain the balance. And the more ways that a molecule can vibrate, the better able it is to absorb infrared radiation, and therefore a more dangerous molecule for the climate, for greenhouse effect. But the good news is, at the moment, the average temperature plus 14 degrees. Okay, so that's the radiation coming from the sun. That tells you how it's absorbed. But maybe this is more interesting for us. At the top of the atmosphere, this is the sort of spectrum we'd obtain. But by the time it's passed through the atmosphere, we get these notches here. And that's just due to absorption bands of molecules, mostly H2O, because there's a lot of water in the atmosphere. But maybe 70% is absorbed, 30% is reflected back into space. Okay, well, this is Michelle and I on our favorite holiday haunt in Cyprus, which has 360 days of sunshine a year, they say. That's where we go. Our favorite hotel. And Cyprus receives 2 megawatts of energy per meter squared over 1 year. Quite megawatts of energy. And maybe the right number to remember is that in the desert, when the sun is directly overhead without any clouds, then the amount of energy we would be receiving there would be about 1 kilowatt per square meter. 1 kilowatt on a bright sunny day in the middle of the desert. That was probably lower in Dublin, and it's certainly lower in Manchester than 1 kilowatt. But maybe we're talking about 200 watts per square meter on a sunny day falling onto the Earth. Okay, so how do we harness the solar power? Well, one example are solar ovens, which are quite common in places like India, where they have lots of sun. And you build an apparatus or an oven that looks rather like this, and you put your Sunday joint in the middle. And these ovens can reach temperatures of 150 degrees. So the next time you go camping, then maybe it would be a good idea to take one of these solar ovens to make your Sunday lunch. At Jodrell Bank, we have an outreach session, and we have a dish, a TV dish, if you like, that we've covered with aluminium foil. And in a bright sunny day in Jodrell Bank, you can toast a marshmallow at the focus of the mirror in about 15 seconds. So these devices actually do work. Flat plate heaters. A very simple idea. You have a plate, a few square meters, and it's connected by a pipe, copper pipe maybe, and the sun's rays heat the plate, several hundred watts of power there, and on the top of your roof. And these things have been in operation for a long time, maybe 100 years. It's such a simple system that it's such a reliable system, and it lasts 100 years or more. And these are the devices you'll often see in Cyprus or in the Mediterranean countries. And these devices reach temperatures of the order of several decades above room temperature, so maybe 70 or 80 degrees. So 70 or 80 degrees water is fine for domestic heating, for heating space heating, or maybe for washing your clothes. But we should say that the so-called quality of the heat is not very high. And I'll return to what I mean by quality of heat quite shortly. 80 degrees. But there's lots of physics there. You can imagine that's a great project for a student to work out how to design a flat plate heater and then to minimize the heat losses of radiation, conduction, and convection. So quite simple physics, I suppose, but we've got things like insulation to avoid conduction. We've got covers to minimize convection. And we can play lots of tricks with the radiation. So back to our slide before. So ideally our surface should absorb visible light, but it should not emit infrared. So what we can do is be very clever with our choice of material and get materials, surfaces, which have those properties, which absorb in the visible, but do not, or are poor emitters in the infrared. Well, another step forward is the so-called heat pipe. So a heat pipe is a copper pipe here with a fluid in it. And the idea is if you heat the one end of the heat pipe, the fluid evaporates, carries the heat up. So instead of the heat diffusing slowly along a copper bar, then this gaseous material will conduct the heat very rapidly. So if you've ever handled a heat pipe and you put one end in hot water, you very quickly drop the heat pipe because it heats up so very quickly. Another advantage, you can embody this heat pipe into a glass evacuated vessel. So this sleeve here, so you've lost your convection, you've lost your conduction, and more than that, because you've got a vacuum here, then that surface there, you can have a very sophisticated material which has the properties you wanted, to absorb in the visible, but to have low emittance in the infrared. And these are devices which you see on roofs these days, and apparently millions of these are produced and used in, for example, China. Okay, we mentioned quality of heat before, so let me say something about quality of heat and thermodynamics. So thermodynamics is just a study of converting one kind of energy into another. And it's our job, of course, to convert the heat that we obtain from our flat plate heater or from our heat pipes into mechanical energy. And the important message is that we know it's very easy to convert mechanical energy into heat. All we have to do is to rub our hands together. And we can do that conversion with maybe close to 100%. The hard bit is converting heat into mechanical energy. Energy to drive a turbine, to drive an electric motor, or whatever. So you can imagine that the Industrial Revolution, the 18th century, and people are designing steam engines and better steam engines. So a simple question would be, if you had a ton of coal, how much mechanical energy could you extract from that ton of coal by heating water, producing steam, etc., producing better and better steam engines? But what was the efficiency? What might you expect? What would be the maximum efficiency you could attain? Well, in stepped Sadi Carnot, a young French engineer, and this is one of those examples where the discipline of engineering has brought a fundamental result into physics. And of course, that was the efficiency of heat engines. And there's a schematic diagram of a heat engine. We've got the hot reservoir, which might be a steam boiler. And we've got the cold reservoir. If you've got heat, you want to extract work from that heat, you can't do that until you've got a differential in temperature between the two reservoirs, a hot reservoir and a cold reservoir. So the heat transports down, and some of it you divert, if you like, to become mechanical work. But you must have that temperature difference. And what Carnot found was that the maximum efficiency of work out divided by heat taken from the hot reservoir was this simple expression, unity minus Tc, the cold reservoir over the hot reservoir, in absolute temperatures, of course. Well, the cold reservoir is invariably going to be the ambient temperature, 20 degrees C. So, for example, a cooling tower at a power station, that is going to be 20 degrees or so. And so this graph here shows what efficiency, the maximum efficiency, we can get from the temperature of the hot reservoir. So at 450 degrees, the maximum efficiency would be about 60%. So you can see the hot water at 80 degrees is not going to provide us with useful mechanical energy. What we need to do is to strive to get the hot reservoir just as hot as possible. So that's why nuclear power stations have a core which have increasingly high temperatures to increase their efficiency, and why jet engines are run at higher and higher temperatures to maximize the power coming out of the jet engine, and therefore the development of new materials. So 80 degrees is okay for heating, space heating, washing your clothes. It's not so good for mechanical energy. So what's the solution? Well, the solution is to concentrate the light with a lens and a mirror to get higher temperatures. And so we get devices like this. So now we're talking about power on an industrial scale. And we have, for example, in the Mojave Desert, we have these mirrors, which are kilometers long. And at the focus of the mirror, there will be a pipe. So the heat is concentrated by a factor of 30 or times 100. And so that water is going to go to 400 degrees. So now we've got water at a useful temperature that we can produce mechanical energy. So that's one way to do it. Or the other way is to have a so-called solar tower, where we have the central receiver with the boiler, many mirrors in the desert, which are then focusing the light onto the boiler. And in this case, rather than use water, they're using molten salt. And in that way, they can achieve much higher temperatures, 600 degrees, therefore higher efficiencies. And the salt is very useful because it's got a very large thermal capacity. So you can store a lot of heat, thermal energy in that salt. What you can also do, which is very important, is to store that hot salt. And there's an important fact here, an important message, that it's much easier to store thermal energy than it is to store electrical energy. When you think about storing electrical energy, you're aware of the difficulties. It's very hard to store lots of electricity. Well, you could use, for example, a lead acid accumulator, which are fine for small applications, but on an industrial scale, it's hard to store electrical energy. Much easier to store a big cylinder of hot salt. Okay, and we can use photovoltaic cells. Well, we're very familiar with these pictures of houses with solar cells on the roof. But now, of course, this is done on an industrial scale where you have solar panels of many square kilometers of area, producing, for example, this one here produces 14 megawatts of power, so quite a lot of power on an industrial scale. But the point I'd like to make here is that solar cells have this huge advantage, that the energy is converted into electricity directly, and you avoid the thermodynamic limitations of heat engines. So solar cells can produce electricity. And maybe that's why you see many more solar cells than hot plate heaters here in Ireland and in the UK. So, what's happening in a solar cell? These are based on semiconductors, and this is a sketch of the energy levels of a semiconductor, where we have the valence band and the conduction band. And the simple idea is that a photon comes along and it promotes an electron from the valence band into the conduction band. And that band gap, the energy gap, is all important. In a semiconductor, the band gap will be about 1 electron volt. And if you think that a visible photon has got the energy of about a few electron volts, then solar energy, solar photons, have got enough energy for this promotion. Well, silicon is just slightly more than 1 electron volt. So that means any photon with an energy, if we do this, about 1 micron is enough to promote an electron from there into the conduction band. Just as an aside, if you're an insulator like diamond, that gap would be 5 electron volts. If you're a conductor like sodium, it would be a very, very small energy gap. So that's what we need to think about. We're going to promote electrons from the conduction band from the valence band to the conduction band, and those photons need to have sufficient energy to do that. And then in the solar cell itself, we've got a junction of a p-n junction. So these electrons which are produced in the conduction band essentially flow from one layer to the other through an external circuit, so they can drive a kettle or our electric light bulb. If you like, there's a potential difference between those two layers, the p and the n layers. So if you produce the electron, it will come to the lower energy in the other layer. It's perhaps easier to think about the photoelectric effect. In the photoelectric effect, you've got a surface, metal surface, in comes the light, you produce a photon, you have a high positive potential, and the electron's drawn to it. But in the p-n junction, that voltage difference is built in, if you like. Okay, Well, it's not quite as rosy as that. That picture's not quite as rosy as I'm suggesting, perhaps. Because not all of the photons in the solar spectrum are useful in producing electrons. So if that's our spectrum of solar radiation, this is in the green, peaking in the green, where our eyes are optimum, 1 or 2 electron volts here. Then these electrons at long wavelength simply don't have enough energy to cause promotion of that electron. These photons here, if you like, have too much energy. So when they promote the electron from the conduction band into the valence band into the conduction band, the high up in the conduction band, they fall down to the bottom of the conduction band and they lose their energy through heat. They simply heat the crystal. So their useful energy is actually converted into useless heat. So it's these electrons, these photons in the middle, which are producing power from the solar cell. And when you work out the details of this, then the maximum efficiency for, say, a silicon solar cell would be about 25%. 25%. So we're kind of getting back to the efficiencies we had before for example, solar cells or even internal combustion engines of the order of that sort of efficiency. So that is what. So this is a basic limitation of a solar cell. But there are ways to circumvent this difficulty. Some clever ways. And one way is to have a multi-junction solar cell. So now what we have are layers of semiconductor, gallium, indium phosphide, gallium arsenide, and germanium. And these all have reducing band gaps. So the top one absorbs the energetic, the blue photons. The less energetic travel through. The green ones are absorbed by this middle cell junction, and the lowest energy are absorbed in the germanium cell. So in that way, we actually, with the 3 slices, we can take out 3 slices of the photon energy and get a much higher, use most of the available photons to convert into useful energy, useful power. Now, they're fairly complicated things, but if you are building a satellite and you want a solar cell to run your satellite, then you're going to use sophisticated devices like multi-junction solar cells. Or you might just think more obvious, I suppose, and just collect as much light as you can and focus that onto your solar cell. Obviously, that gives you more photons, therefore more electron current and power, but there are also advantages that the power you get is a higher power than before. So maybe in an ideal world, you'd have a combination on your roof of both of those types. You would have your hot plate for hot water and your solar cell for electricity. So, in a simple model of a solar cell on a house, what sort of power might we expect? Well, on this simple drawing here, what would we have? Well, there's our 1 kilowatt in the desert, but let's multiply by an optimistic factor of 1/2 what we might achieve on a sunny day. The area of the solar cell might be 4 meters by 10 meters, and the efficiency of the solar cell about 20%. So when you add all that together, you might achieve a total power of 4 kilowatts. Let me just say something else about materials that are used for solar cells. So there's lots of research going on in different materials. Quartz is still the favorite, I suppose, because it's such a mature industrial process now to make silicon crystals, that they still retain the main market. But of course, people are looking at other materials, organic materials, but they never achieve great ideas because you can print them with a printer in any shape you like, but the efficiencies are never as high as 20%, at the moment at least. They're the order of a few percent, maybe 5%. And another trick is to use a quantum dot. Okay, so a quantum dot is a piece of semiconductor which has a dimension of maybe 10 nanometers in all directions. And so it's really a quantum well. So we're familiar with the idea of a stretched string, and you plug the stretched string so you can only get certain frequencies of standing waves. Well, it's the same thing in quantum mechanics. If you've got a small three-dimensional sample of silicon, quantum mechanics says you can only have certain frequencies of standing waves. And so you can, in that way, by changing the size of the quantum dot, you can actually change the energy levels in the quantum dot, and therefore you can tune the band gap. So you can actually produce band gaps, as we said before, of multiple band gaps, obtaining maximum power. Okay, so we said before that the sun doesn't shine anymore. So, of course, a big problem is energy storage. And there's another problem, and that's that energy demand is strongly peaked. So when you're watching Manchester United play Liverpool, and half time, when we all put the kettle on, then of course the demand will spike. So we've got two problems now. We have the sun not shining, or the wind not turning the turbines, and this peaky, lumpy demand on the national grid. So what we need is storage. Well, just as a sideline there, let's not forget fossil fuels. For energy storage, what you need is to put a lot of energy into a small space or a small mass. You need to be able to switch it on very quickly because of those demand requirements. And also density. And also you want the conversion efficiency to be very high. As much energy as you put in is what you get out, or as close to that as possible. Well, let's not just forget fossil fuels for a moment. We've been using those for millennia. They have a high density of stored energy, 5 kilowatt hours per kilogram. So your kilogram of wood would be equivalent to your electric fire for 5 hours. They can be switched on, burned fairly rapidly. And of course, they do originate from solar energy through photosynthesis. But now we want solar energy, we want industrial scale. Well, I mentioned one before, and that was the storage of hot salt. That's a very efficient way to store energy, because it's hard to store electrical energy. Batteries, of course, again, a lead-acid accumulator can store a huge amount of energy in a relatively small space. So you'd say that an accumulator has a very high power density. And batteries are okay for low power applications. But if you want industrial scale energy, how do you do that? Well, perhaps the most effective, the most cost-effective way is pumped storage hydroelectric power. A very simple idea. You have a hydroelectric plant, you let the water flow down the pipe, you generate electricity, but then at night, when the power demand is low, you reverse the turbine and the water is pumped back up again for use tomorrow in the high demand periods. And this is cheap. A good example would be the Festiniog Electric Mountain in North Wales. And its most important advantage is that you can store a huge amount of energy. Although the power density is quite low, you've got a large volume of water Therefore, you can store a large amount of energy. And of course, you can switch it on at the flick of a switch. So when it's half time on Coronation Street, you flip your switch and there's your power. But another industrial-sized method is compressed gas energy store. So we would have a salt mine, a disused salt mine, and the simple idea is that we compress gas and store the compressed gas in this salt mine. And then when we need the energy, we simply release the compressed air to drive our turbine. And maybe you've never thought about this before, but really pressure of a gas we can describe dimensionally, if you like, as energy per unit of volume. So high pressure gives you high energy. Okay, so in summary then, solar power increasingly makes very valuable contributions to our energy needs. It's renewable and environmentally friendly. And there's lots of science, lots of physics and technology involved, and lots of scope for young minds to develop new ways to use solar energy. Thank you for listening.